This lecture deals with the MER design of a hen where stream splitting is not required. We have already seen MER design of hen where stream splitting is required. So, we have completed that part. Now, I will take up this problem which is given in table number 6. This stream problem will be considered for MER design and then the same problem will be extended for non-MER design. In the non-MER design, we will identify the loops and then we will break these loops. Now, let us start by taking the problem. Now, I have opened up the hint software. Now, we will go for the feeding of the streams, streamed H1. The supply temperature is 160. The target temperature is 60 and the value of MCP is 2.5. Stream number 2, this is H2, supply temperature is 140, target temperature is 30 and this value of MCP is 1.5. Then we go to C1, the supply temperature is 20, target temperature is 125 and MCP value is 2 and the fourth stream C2, supply temperature is 80, target temperature is 130 and the MCP value is 3.5. Now, the H values for these streams have been taken as 2 kilowatt per meter square Kelvin, which is a default value in the hint program. So, I say OK. So, my stream table appears here 160, 60, 140, 30, 20, 125, 80, 130 and the MCP values are 2.5, 1.5, 2 and 3.5. Now, I will directly go for the design. If you want to see the different diagrams, this is the composite curve, this is the grind composite curve and this is the grid diagram which is needed for the design. So, obviously, as I have done in the earlier case, we will try to see the feasibility and the feasible matches. So, these are the feasible matches above and below pinch. Number 3 can be joined with number 2 for a match placement. Number 4 can be matched with 1 and 2 and in the below pinch the 1 can be only matched with 3. So, let us start design. So, we go for feasibility above the pinch. Now, a match can be placed from this table by entering data into this table, or the match can be placed by heat exchanger and add option. This also allows you to fix up the match. Here if you see that I can select the streams and the utilities, cold utilities C1 and C2, there are 2 options, 3 options I can select, and the hot stream, there are 2 hot streams and 1 utility. So, we will have 3 options here. So, I can select the options and then specification type, user supplied enthalpy, and other specification types are also available. User supplied temperatures, enthalpy to complete the cold streams, and enthalpy to complete the hot streams. So, these are 4 options which can be energized, which can be taken up for the heat exchanger design. Here it gives you the inlet temperature. If I click this, this is inlet temperature. Here I can fix up the temperature. Here I can mention that it is a pinch temperature. Here I can say that it is the outlet temperature of heat exchanger number such and such. I can change the heat exchanger number from here, this drop down menu, or I can specify cold stream supply temperature. Now, this is cold stream outlet temperature. If I click, then I can provide the temperature, or I can say that its cold stream outlet temperature is the pinch temperature or inlet temperature of a certain heat exchanger, or cold stream target temperatures. Similarly, here for the hot streams, I can say the hot stream inlet temperature to the heat exchanger is this, I can mention here, or I can say that this is from the pinch, or I can say this is outlet temperature of such and such heat exchangers, or hot stream supply temperature. Similarly, outlet temperature if I click, so these options are available. Now, by selecting these options, I can place a match, or a easier option for at least placing a match is to go to this table and start placing the pinch matches. So, we will take up the easier option, and now what we will do, we will match the streams. So, above the pinch, the rules are number of hot streams should be less or equal to number of cold streams, and above the pinch I find that there are 2 hot streams and 2 cold streams. So, this criteria is fulfilled. The second criteria is MCP of hot streams should be less than MCP of cold streams. That means, a higher value here will match with a lower value. That means, 2 can be matched with 1.5, or 3.5 can be matched with 2.5 as well 1.5. Okay. Now, let us start placing the heat exchangers. I can match this 160 to 60 stream, that is stream number 1, with this stream, because here this is 3.5, this is 2.5. So, 2.5 and 3.5 I press. So, the color changes. It shows that it is a feasible match. Now, to place the heat exchanger, I can click it again and I can say OK. It places a match, and this match can be placed as well using this heat exchanger add option, but I am taking a shorter route to place the at least pinch matches. So, its entry temperature is 90 and its capacity is 175. That means, this stream has been ticked out because it reaches 130 degree centigrade. And if I see here, it is 175 and 160 minus 90 multiplied by 2.5 will give me the capacity of this heat exchanger. Now, I place a second heat exchanger between 140 to 30 and this is 20 to 125 between these 2 streams. So, I can go to the stream, go to the feasibility, go to the above the pinch and these two can be matched because 2 is greater than 1.5. So, I click here, I click here, it changes, and then I click here and say OK. So, it puts a heat exchanger here. Now, if I see, I can drag down it to here, drag down it to here. Now, I see that the outlet temperature of this heat exchanger is 117.5, where it has to go to 125. That means we need to put a heater here. But before putting this heater, we will first place the pinch heat exchanger in both parts, that means above the pinch and below the pinch here, and then we will put the heaters and coolers. So, let us try to put our pinch heat exchangers here. So, I go to stream, then visibility, go to the below the pinch. Now, the rules are number of hot streams should be greater than number of cold streams. So, this is satisfied. We have 2 hot streams, 1 cold streams. So, do not have to bother about this row. And MCP of hot stream should be greater than MCP of the cold stream. Now, if I see this, then I find that I can match this with this, but I cannot match this with this. So, let us first match this with this. Now, I can click this and then I say OK. So, it places a match. Here the 75 kilowatt is the size of this exchanger, that means capacity of this exchanger. I can place it here. Now, obviously, if I see this, then its outlet temperature is around 42.5 degrees centigrade. So, from 42.5 degrees centigrade to it has to be cooled down to 20 degrees centigrade. So, there is a possibility of putting the match from here to here, but if I see this, my rules does not permit. Now, we have to little bit analyze these rules. These rules are for pinch heat exchangers. That means, for the pinch heat exchangers, these rules are sacrosanct. That means, has to be followed very rigidly for pinch heat exchangers. But if it is away from the pinch, these rules can be slacked. That means, somewhat we can slack this rule and put the heat exchanger. The only criteria is that it should not violate delta T minimum criteria. So, let us try to put a heat exchanger. So, we do not go here, we take up this heat exchanger, add option. So, we put a add. So, my heat exchanger number 4, this will be placed between 3 and 2, 3 and 2. So, my cold stream is 3, and my hot stream is 2, and the enthalpy here available is around 45 watt. This can be computed from the outlet temperature of this heat exchanger to 20 degree centigrade, and the outlet temperature of this heat exchanger, which I will be put, the inlet temperature to this heat exchanger will be 20. So, I go to 20 degree centigrade here, and for the hot, the inlet temperature will be the pinch temperature. So, I put it 80. So, I now place this heat exchanger. So, I find that this inlet temperature is 42.5 and the outlet temperature is 20. I think somewhere tools exchanger format, if I go, then hot stream outlet temperature, hot stream inlet temperature and cold stream inlet temperature also. If I click it, then if I say OK, I will get all temperatures. So, here it is 80 it is entering and 50 it is going out. So, you need a cooler here. Here it is entering at 20 degree centigrade, going out at 42.5 degree centigrade. So, this stream is ticked up. So, this stream now requires a cooler. So, if I go to here and place a heat exchanger, the number of the heat exchanger will be 5. This is the 5th one. I will be using cold utility because it is a cooler, and the hot stream is number 2 because this stream has to be cooled down. Now, the enthalpy of this is 45 watt. I can calculate it out because it has to be cooled down from 50 to 30, and the hot outlet temperature has to match to 30, or I can say that the hot stream target temperature. So, I put 30 here, I say OK. So, I put a this is 40 by 45, this shows why the hot inlet temperature is 60, no, the hot inlet temperature is 50, or I can say the outlet temperature of heat exchanger number 4. So, if I say OK, so this matches now. Now, this shows you the feasible hen design, which is a MER design. So, we finished 2 hen designs, one in which splitting was required, another in which splitting was not required. Now, this heat exchanger design will be further improved, and we will identify the weaknesses of this design. We, from the units targeting, we know that if there is a loop, then it consumes 1 extra heat exchanger per loop, and if the number of heat exchangers are more, then obviously the cost will be more. So, we have to do a trade off between the heat exchanger, number of heat exchanger and the TAC. So, we will identify the loops, we will break the loops, and once we break the loops, we will find that it causes delta T minimum violation, and to eliminate that delta T minimum violation, we have to pass the heat from heater to cooler and rectify it. I have forgotten to put the heat exchanger, the heater here. So, heater has to be put here. So, let us put the heater here. This is add heat exchanger. I go for the 6th number of heat exchanger, because 4 heat exchangers are there, one cooler is that 5. So, next is the 6th one. So, it is put on 3rd stream, that is C1, and this is the utilities, and the enthalpy required is 15 kilowatt, that we can calculate from this 125 and this, and its inlet temperature, hot inlet temperature is the outlet temperature of heat exchanger number 2. It is not giving, so it do not go to this. Between this and this we am putting. So, what the inlet temperature is 175 and the outlet temperature is 125. Outlet temperature, let us fix 125. Okay. So, I say okay. There is some problem it has created. 90, oh, it has changed this. Oh, this I have to delete some mistake we have done. This temperature has changed. 80, 50. No, this has changed. I have to correct this. This is the proper place. So, we again try this heat exchanger add. This is 6th number heat exchanger. This is between hot utility and cold stream is number, hot utilities, cold stream is number 3 stream. Enthalpy is 15 and this is a cold stream. So, the inlet temperature is outlet temperature of the hot stream. Outlet temperature is not giving. I can say the cold outlet temperature. Outlet temperature is cold 125. So, if I say yes, let us see what happens. Again some mistake has been done. He is taking this to be a heat exchanger, and between this I delete this. Cold stream is 3rd. This is utilities. Enthalpy, this is selected user supplied enthalpy. This is 15 kilowatt. The inlet temperature is outlet user supplied enthalpy. Oh, this is number 6. This is 3. This is utility. Enthalpy is 15. Inlet temperature 175, it is 117.5. Outlet temperature is 125. Let's put it okay now. Oh, this was creating problem. This is number 1. This is creating problem. Delete. Yes. Okay. That's why there was a problem. Oh, this has been gone. Let us put again this add, this is stream number 3, this is 6th number, this is stream number 3, and this hot stream is utility, enthalpy is 15, outlet temperature is 125. Now it should work. What has happened again? And at 60 to 60. All this 90 to 60, this is 50. This temperature has changed somehow. 250, how this has become. Between 1 and 3. In order to eliminate the delta T minimum violation, we have to pass the heat from heater to the cooler. In this case, I have forgotten to put the heater, so now I will put the heater in stream number 3. So, we go to the heat exchanger, say add. So, this is cold stream is stream number 3, hot stream is the utility, and the enthalpy is 15, and the inlet temperature, it is cold inlet temperature, is 117.5. Let us see. Again I start this heat exchanger add. I had committed a fault, I had not given a new number to the heater. So, I put the new number, that is 6 now. Cold stream is 3, and hot stream is the utility, enthalpy is 15 and the inlet temperature is 117.5. So, now it is correct. So, we have a heater here. So, this finishes the design of a heat exchanger when stream splitting is not required. Now, we will touch a new topic, which is loops and path, and we will show that this heat exchanger, which is a MER design, can be improved by breaking the loops inside the heat exchanger network to decrease the number of heat exchangers. So, the same problem we take, that is the 4-stream problem, too hot and too cold, to demonstrate the loop and path identification and breaking, which will improve this heat exchanger network, but the design will convert from MER design to a non-MER design. So, we have to first identify the loops. So, we go to the loops and path and then press the search. So, it identifies a loop here 2 to 4, and then if I press this next, it identifies a path from the heater to the cooler, and the path is this. If I again press next, it identifies another path from S6 to 2 to C5, and if I press next, it identifies the loop. Once we have identified the loop, then our job is to break this loop. This loop will be broken if I eliminate one of the heat exchangers of the loop, either 2 or 4. It is better to eliminate 4 because its heat duty is less. So, next will be to go for add. So, we see here this is the loop 4 to 4, and if I press this OK button, then yes button, it tells that my loop has been broken because the heat duty of 4th number heat exchanger has become 0, but there is a delta T minimum violation here because my delta T is 10 degree. This temperature, which is 60 here, should have been 67.5 to maintain the delta T minimum, which is 10 degree. Now, there is a clear cut violation of the delta T minimum, and hence this design is not correct. To make it correct, I have to restore the delta T minimum criteria. That means, I have to increase this temperature to 60 degree centigrade. Now, this can be done by passing heat from H6 through heat exchanger 2 to this cooler C5. Now, this can be shown by this PPT. What has happened here, there is a delta T minimum violation. I have made this 0 to eliminate this heat exchanger, So, the capacity of this heat exchanger or the heat load of the heat exchanger increases to 75 plus 45 to take care of it, but once it takes care, there is a delta T minimum violation. So, the heat has to flow from here to here. Now, in this I show that I have to add x amount of heat to the heater, which will decrease the load of this heat exchanger by x amount and increase the load of the condenser or the cooler by x amount. And to restore this delta T minimum, here I have written T1. So, the value of T1 should be 67.5 to maintain a delta T minimum of 10 degree centigrade. So, the question is to find out the value of x when T1 is 67.5 degree centigrade. This is the job now. So, we see how this can be computed using hint. So, we go to the loops and path again, we press add and we now press the path. So, H6, then 2 and then C5. So, this is the path, it will move from H6 to 2 and 5. You have to cancel this, we go for analysis. Here this is, it is moving from C6 the H6 and then to 2 and then to 5. Now, the important things which I have to analyze is that this temperature, this is the exit temperature, hot exit temperature from heat exchanger 2. I have to also see the enthalpy of heat exchanger 2. I have to also check the enthalpy of heat exchanger 6. I have to also check the enthalpy of heat exchanger 5. So, by this switch add, I will select those. So, I go to the heat exchanger, go to the heat exchanger number 2, I take hot stream target temperature, press hot stream target temperature and then say OK. And then again go to heat exchanger, exchanger number 2, then enthalpy, then OK. Then again I go to the heat exchanger, take heat exchanger number 6, say enthalpy, press enthalpy, and then again I go to the heat exchanger number 5, which is the cooler, then enthalpy and then OK. Now, once I have selected my required parameters, to find out the amount of heat we should move from H6 via heat exchanger 2 to this cooler to maintain this delta T minimum, which is now being violated, then the rest is to run this analysis. So, we have run this analysis. It says that if minus 2.727 kilowatt is added to the already the load of H6, then the load of H6 becomes 12.2727, and if it is 12.2727, then this temperature, which is 60, is 58.1818. So, it is not going to solve our purpose, because the gap between 57.5 and here to maintain a 10 degree centigrade gap, this should be 67.5 degree centigrade. So, now we search for the value. So, we see this is 60, this is 61, I have to go up to 67. So, this is 67.2727, which will not do because it should be 67.5. So, I find here. If I add 10.9091 kilowatt to this H6, then my temperature becomes 67.2727. If I add 12.2727 heat to this, deduct from this and then add to this, then this temperature becomes 68.1818. The 68.1818 is okay because it provides me a delta T of 10 degree centigrade, which is required. Now, the value of heat which should be added will fall between this and this, and this can be calculated using a linear interpolation. Now, we see here, if I use linear interpolation, the value of x comes out to be 11.25 kilowatt. So, these values are available from hint. We can go for a linear interpolation and find out what should be the value of x, and it comes out to be 11.25. Then I can put the value of x here. So, it is 15 plus 11.25, 15 plus 11.25, which comes out to be 26.25. So, my heater load becomes 22.65. Now, the loading of this heat exchanger becomes 120 minus 11.25, which comes out to be 108.75, and the load of the cooler is 45 plus 11.25, which comes out to be 56.25. Now, if this loads are changed of this heater and this heat exchanger and this cooler, then T1 becomes 67.5, and hence the delta T minimum violation is removed. So, this way we can calculate the amount of heat which should be added to these heat exchangers and then maintain the or eliminate the delta T minimum violation. Now, you can also see through this add diagram what is the cost, change in cost. You can also see that area and cost, how the area and cost of the heat exchangers once their loads are changed are varying, and by doing so we can find out whether I am gaining something by breaking this loop and passing heat through the heat path, or we can go to the heat exchanger and we can go to the results, and then we can one by one we can see the specifications or area and cost. Here the cost is given and here the area is given. So, by knowing this cost we can find out whether it is beneficial to break the loop and pass heat through the heat path from heater to the cooler. If we do not get any benefit by breaking the loop, it is better not to go for it, and keep the hen as it is. So, this finishes loops and path. Loop and path identification and breaking can be done using software hint.